electrical. This is how we get all of our power for our lighting, our appliances, and any other electrical equipment. Can you all see the screen? Okay, good. So the system we are focused from an inspection point of view on the 120 240-volt system that powers the house. And so that system basically begins at the point where the uh, utility company connects to the home and then continues throughout. So everything that we inspect primarily is going to be a part of this 120 240-volt system. Let me change this. So, what is in scope for us as far as our inspection? The service drop, our service lateral, so that's where the utility drops in the service entrance conductors, those are the wires that we actually bring the power in with. Our service equipment, which is the our disconnects, how we control the flow, our panel boards, our circuit breakers, grounding and bonding system, our branch circuits, our GFCI protection devices, as well as our receptacle switches and light fixtures. So again, to my point, what I was talking about last week of how we can be in the kitchen and there be electrical components that we have to inspect. Again, our GFCI falls under the electrical system, but for your actual inspection, it will show up in the kitchen and in the bathroom or maybe on the exterior of the home. So these are the different components that we have to evaluate and sometimes operate our GFCIs and different things like that. Obviously, this is one of the most important systems. We're going to be looking for safety issues primarily when it comes to our electrical system. We don't have to sort of worry about the low voltage systems. These are like our doorbells. If you have like alarm wiring and different things like that, they operate at a lower voltage, and that's technically outside of the scope. Usually, I if they have a standard doorbell and not like a ring or something like that, I will test it and confirm, that the audio portion of it was working. But those lower voltage systems are typically outside of the scope. I basically covered the SOPs with that. So when we get down to the nitty gritty, what is electricity? Electricity is simply the flow of electrons. So these are those tiny particles that are charged and they move through a path or a wire. When these electrons are flowing, we call that flow electrical current. Okay, so in our homes, that movement happens within a circuit. A circuit is just a closed path that allow the electrons to leave the power source, go do the work at our light or whatever the case may be, and run and return back to the source. These circuits have to be complete in order for electricity to flow. Think of it as it's a continuous loop. So electricity is always continuously flowing in this continuous loop. There are three main parts. You've got your hot wire or your energized conductor. And this again carries that current or carries that circuit. And then you have your load. This is the part of the circuit that's actually using the electricity to do something like your light bulb or your refrigerator. That is the actual load. And then we have our neutral wire, which is called the grounded conductor. And this returns current back to the panel, which completes the circuit. Because if you think about it, like practically, you would think that electricity would come from whatever source, go to the load, power it, and that would be it. The electricity is used up, but it doesn't work like that. After it powers the load, it goes back or it wants to flow back to the source. Okay. So it doesn't start in your actual electricity, doesn't start in your actual house. It is sort of create not sort of, but it is um generated at a power plant. The power plants use different energy sources to make the electricity, and then once it's generated, the electricity moves into the transmission and the distribution system. This is what we call the grid. Okay, so that's how we generate electricity. And while it is on the or as it travels on the transmission lines through the grid, there are substations in our neighborhoods and in our areas that basically step down or lower or reduce the voltage so that it's safer to distribute. And then we have distribution lines. These are our smaller power lines that run through the neighborhoods to literally deliver the power. And then we have transformers. Those are like the gray sort of, they look like almost like a smaller version of a garbage can. You see these on utility poles. The transformers reduce the voltage down again to our 120, 240 volt system for residential use. So we use the 120 volts to power our outlets and our lights, and then we use the 240 to power larger appliances that require more, like dryers, your stove, ACs, different things like that. So just know that by the time when the power leaves um the power plant, it's at like thousands and thousands, like 13, 15,000 volts. That is way too much for what we need in our residential homes. And that's why they're constantly at the substations and then at our transformers, they're constantly stepping down the electricity to make it suitable for our residential homes. So we're going to think about this like a water hose analogy. We talked about plumbing. Who's calling me right now? We talked about plumbing, so we know that we're kind of familiar with how that works. So we can use the same analogy. A electrical circuit is like water flowing through your plumbing pipes. So electricity flows along wires just like water flows through plumbing. The key parts of this, the three main key parts of this system, this electrical system, are your voltage, current, and resistance. Okay. So let's start with voltage. Voltage is the force that pushes electricity through the wires, the force. So without voltage, your electricity wouldn't move. It is obviously measured in volts. So when we say 120, 240 volt system, that is what we are talking about, the force that's pushing the electricity along or through the wire. So if we were to compare it to the water hose, the voltage is like the pressure of the water. You know how you can increase or decrease the pressure? That is akin to voltage. If you have more pressure, then more water flows through through the hose. Same thing with the voltage. More in a wire, more voltage pushes more electrons through the conductor. Every device is designed for a certain voltage. This is called a voltage rating. Okay, so like you look at a light bulb in your house and it might be marked 120V. It is built to handle 120 volts. If you plug it into a 120 volt outlet, you're good to go. It'll function correctly and safely. If that voltage is too low, it may not power the light at all. If it's too high, you may overheat, blow the device out, and basically have a fire on your hands. So in our homes, most of our lights, our outlets, and like smaller appliances, they are built to handle 120 volts. Okay, the larger items, your dryer, again, your AC, water heaters, ovens, all of that are designed for a 240 volt system. So remember when I said our low voltage systems, those use 12 to 24, like your light, your doorbells, those little lights that you can put out in the yard, all of those are low voltage systems. So 12 to 24 volts compared to the 120 that it takes to actually light and use our outlets. Next, we've got current, which is the current is the amount of electricity that is flowing through the wire, and it is measured in amps. The more amps, the more electrons are moving. So your voltage pushes and the current flows. So in our water hose analogy, if the voltage is the water pressure, then the current is like your how many gallons are flowing per minute, or your flow rate. If you have more voltage, more push, then you have more flow. Okay. So current, every wire, breaker, and device has a limit for how much current it can handle. Again, too much current, you will overheat your wires and your devices and have fires. That is why we use breakers, which we'll talk about on Friday, to shut circuits off when they go too high or when they exceed the rating. Okay. So your microwave draws 12 amps of current while it is running. Your dryer may draw 25 amps while it's running. So your breaker, your wiring, and your outlet have to be the proper size in order to handle the load. So that's one thing that we are looking to verify during inspections. Our breaker sizes, again, we'll talk about this on Friday, but say a 20 amp breaker, it has to match. There has to be a certain wire size that it use. So we use a 12 gauge wire for our 20 amp breakers. Okay, so again, we'll get into that on Friday. But that is why current actually matters or is important. Too much current, you'll have too much heat and you'll have a problem, pretty much so. And then our last one is resistance. So resistance is anything that opposes or slows down the flow of electricity. Resistance is measured in ohms. OHMS. The more resistance that you have, the less current flow that you have. So like if you have something in your pipe, debris in your pipe slowing the water down. Okay, so Ohm's law, let me go to the next one here. Ohm's law is the basic rule, basically, that explains how electricity acts within the circuit. And it also explains how all of these three, voltage, current, and resistance, all affect each other. If one changes, the other must change too. So, again, if we have our voltage, our push, or our force that's pushing the water through the circuit, and then our current, how much electricity is moving through the circuit measured in amps, and then resistance is what could slow that flow of current down. So this is the formula. So the amount of current, because I here equals current, the amount of current depends on how much push or voltage there is and how much resistance. Okay, so your voltage pushes the electricity, resistance slows down the electricity, and the current is what actually flows through the wire. So if your voltage goes up and your resistance stays the same, what happens to the current? That's correct. It goes up. If resistance goes up and voltage stays the same, what happens to the current? It stops. That's correct. This again is the technical side that you do not necessarily need to know for your field work, but you need to have an understanding of it for test taking purposes. So let me go to the next one here. So let's talk about now how we get electricity, how it actually gets to our home. So I said that most residential homes in the US have a how many vote system? They work over how many vote system? 120. Is that what I said? 120, 240. 120, 120, 240 volt single phase electrical system. So that's important because this system allows us to run our small devices on, again, on 120 20 volts, and then our larger items on the 240. Okay, so 120 volts are for our normal household circuits. Think your outlets, lights, small appliances, and the 240 volts is for heavy appliances. Okay, so voltage is what? Explain voltage.
So voltage is the amount of current that is pushed through the wires.
The force, correct. Force or pressure that's pushing the electricity through the wires. Current is what, Luis? Current is what?
The flow rate.
Correct. What is it measured in? Current is measured in what? Help him. Amps. Write that down, Luis. Current is measured in amperes or amps for short. When we talk about conductors, or when you see that word conductor, all that means is wire. Okay, so don't let that confuse you. A conductor is simply just a wire. Okay, our neutral or our grounded conductor does what, Bree?
I just read it. I forgot.
Help her.
Carries a load.
Carries what?
It carries the current, the load.
Carries the current where?
To the device that's
the neutral.
I'm sorry?
The neutral.
The neutral returns to the source. Oh, returns it to
The neutral returns the current back to the source after it completes the work at the load. Okay? And the ungrounded conductor or the hot conductor does what, Miss Sims?
It's the power. The
What is it carrying? And where is it going?
It's carrying the amps to the device.
Correct. It's carrying the current, which is measured in amps, to the device. Most for our homes, the minimum residential service requirement is 100 amps. So your home has to have 100 amps of service capacity. That is the very minimum. That is a test question. You need to memorize that. 100 amps. Now, entering the house, the conductors that come into our home. A typical service entrance cable, the cable that's entering our home, will contain 2 hot conductors, each carrying how many volts?
120.
That's correct. Each carrying 120 volts to neutral, and then one neutral conductor or the grounded conductor, which serves as the return path. Neutral is the return. Okay. Typically, these wires and everything we'll learn conductors are color coded. So, hot conductors are typically either black or red, or they'll be black with a red stripe. Your neutral is either a white or gray, and then your grounding wires are bare copper or green. So, let me stop this. I want to draw out our.
You repeat that again?
Which one?
The hot is red or black, the neutral is white
Or gray.
or gray.
And your your grounding are bare copper or green.
What's bare copper?
Just copper wire.
Okay.
Actually, I'll draw it on the next one. Okay, so we're gonna talk about the 7 steps of how power enters the house. So this is our step by step. So on this diagram, it's not actually shown here, but step 1, the power starts at the utility transformer. Okay, so again, the electricity is produced at the power plant is at too high of a voltage. Before it can come to our house, it has to be stepped down, and that's what our transformer is doing. You can have your electrical service wires come in overhead. We call that an overhead service, or they can come in underground. Okay. So the first step is the power starts at the utility transformer. Now step 2 is what we can see here in the diagram. From the transformer, we have our service drop conductors. If we're talking about an overhead service, we have our service drop conductors. If it is an underground service, that is called a what? I thought y'all said y'all read. An underground service is called what?
Grounding, something.
No.
The conductor.
Service lateral. If you're getting your service from the electrical company and it's underground, that is called a service lateral. Okay, so step 2 is our service drop conductors, or they're coming from the transformer. So that is what we have here. We have again 2 hots and a neutral. Step 3 is the service point. This point is where the ownership and responsibility change. Everything before the service point belongs to the utility. Everything after the service point belongs to the homeowner. So the service point, literally, if you were looking at it, it looks like a splice. So you've got your cable, which has 3 conductors, and it is spliced together with another set of conductors. That splice point is the service point. It's where the responsibility for the homeowner begins. You will need to know that. Step 4. After the service point, the wires become the service entrance conductors. You see here, they are service drop. They're dropping down from the transformer. They splice or connect with these service entrance conductors. These are the conductors that will be entering the house. These service entrance conductors pass through a weatherhead or a gooseneck before they go down the service mast. A service mast is just conduit to protect the wires. One thing to note, before the weatherhead, your newer requirements require a drip loop. This is just literally a drooping or a downward loop of the wire right before it goes into the weatherhead. The idea is that this will allow rainwater to drip off of the cable before it goes into the weatherhead. So at step 4, you now have service entrance conductors, you have your drip loop, you have your weatherhead, and the conductors are going down the service mast. Bree, I ain't seen you look down. You taking notes? Cause I'm gonna ask you for these steps. You got to know that.
Taking notes.
Oh, okay, you got to know I'm gonna ask for the steps.
Yes, I got you.
All right, bet. Step 5, the meter base, right here, which is what holds The utility meter. Of course, we got to have a meter so they can charge us. So the meter is actually inside of the meter base. And again, it measures how much electricity we are using. Power flows into the meter, passes through their little meter counter system so that they can charge us. Meter bases, there's a shape that gives you sort of a clue about the power of the house. Back in the day, the meter bases used to be round, and that meant that the house had a service of about 60 amps, which was way low. The square meter bases like this are the newer standards. This indicates a service of about 100 amps. And then there's a rectangular meter base that denotes a service of 200 amps on your newer homes and things like that. Okay, so those are just a sort of indication again before you get into the house to get to the panel to see what is rated. If you have a round, you know you probably have an inadequate system. You're not getting enough power. So it's going to help you to estimate what the capacity of the home is. And then step 6, after leaving the meter, the power is going to enter the service equipment, which is the control center for the electrical system. After leaving the meter, the power enters the service equipment. After leaving the meter, the power enters the service equipment. What is service equipment? Panel board. Okay, okay, I'll take that. The service equipment is the main disconnect, the panel board, or any basically means of disconnection is what we refer to as service equipment. So this is the point where all of the power to the house can be shut off, sort of like the main water shut off in the plumbing system. The service equipment here is where the power is also distributed throughout to the individual branch circuits, which branch circuits, if we were talking about plumbing, it would be like our distribution lines, how we have our hot water that flowed through the distribution lines to our different fixtures. Well, that's what our branch circuits do, carry power to all of our different outlets and lights and different things like that. So that is step number 7. From the service panel, electricity is divided into branch circuits that distribute power through the home.
What's the wheel?
7.
Okay, can you repeat that?
7.
Yes.
Uh,
Well, 6 and 7.
6 is the service equipment. After leaving the meter, the power enters the service equipment. Think panel. And step 7, from the service panel, the electricity is distributed throughout the home by branch circuits. Each of these branch circuits is protected by a breaker. And it typically powers a specific load or a specific part of the house, like again your lighting and your receptacle circuits for the bedrooms on one floor, one circuit. Your large appliances typically have their own. um so that is step number 7, just basically the distribution of power throughout the home. Are there any questions on those steps?
So let's start on step 7.
Say again.
You said they're distributed by a branch circuit, and you said they have something on their own.
They're protected by breakers.
Okay.
All right. So get a clear space in your notes so that we can draw this diagram together. I'm gonna stop this.
I have a question.
Uh-huh.
So this is for the service drop before service lateral, is there any more steps or less steps because it's coming from underground? Like, does it have any type of loops or anything?
No, because it's like you said, it's coming from underground. Typically it picks up at the meter right before it goes into the house. All right. So give me step one, Philip.
Step one, power is coming from the electricity starts at the power plant.
Starts at the transformer.
It starts at the power plant, then it is transferred to the transformer.
Okay, so I got my transformer. Everybody draw a transformer in your notes. Now, Cola, give me step two.
I think that's about the service the cellular lateral and how it comes into the resting.
I couldn't hear you.
Service overhead or service lateral how it comes into the residential. Again.
Okay, so this is an overhead service. So what's gonna happen?
Overhead service would be the way it comes in maybe via a pole into the house, into over the buildings.
A pole doing what?
The service overhead, which is coming from the street, from the pole outside the street.
Philip already gave me step one. I got that I have the power starting at the transformer. I already got this is my transformer right here. What happens next?
Service drop conductor.
Okay, how many service drop conductors?
It's going to be 2 hot and 1 neutral, which is
Okay.
about 120 volts.
Okay, so these are two hots, and I've got one neutral. 120 volts, 240 volts. Everybody got that? Did you draw that? C. What is step three?
From the service drop, it goes to the service point.
What is the service point?
Is it the service mask? I know it splices.
The service point is a splice. Is that what you're saying?
No. The service point is right before it goes into the service mask, right?
So what did you say about this splice deal?
So it splices into three. This I know the function. I'm trying to picture. It's where the responsibility goes from the utility to the owner.
If I had to visually point it out, what would I be looking for?
There are three, for lack of better terms, like knobs on the splices. I'm sorry, on the conductors.
Well, why you keep saying the word splice?
Cause that's what I remember when you said it. Basically,
Well, what do you remember about the splice?
There is 2 hot, 1 neutral.
Well, I got 2 hots and 1 neutral right here. These are my service drop conductors, right?
Mm-hmm. That's what they call service drop conductors.
These are my service drop. You told me that what happens next in step 3 is the service point. I want to know if I visually had to identify the service point, what would I be looking for?
You would see 3. I don't know the name of them. The only way I can describe them is like 3 knobs on those service drops. On each cable, you'll see like 3 knobs.
Does anybody disagree?
Because that's where it separates. A drip loop?
What'd you say?
You'll see a drip loop, like it'll Drip down.
At the service point? I'm trying to visually identify the service point. If I got up right now and went outside to a house and I was standing at the transformer, I saw the three service drop conductors coming from the transformer, and you all are telling me that step 3 is the service point, what would I be looking for to identify?
You will see 3 like circular knobs between the cables.
Where are the knobs coming from?
It's in my head.
What are the knobs, bro?
She's getting those knobs from the visual, from the.
Oh, from the okay. All right, let's clear this up. Those knobs represent the splice. That's why I kept asking you, what about the splice? This, they look like knobs, I guess, but it is just trying to represent or denote a splice.
Splice separating the responsibility from the utility company now to the homeowner.
Correct. So if we were trying to visually identify the service point, we would look for the splice. It will basically look like 3 wires, and then you'll see like tape. It'll literally look like a real splice, like they have spliced wires together. That point right there is the service point. That is the point that separates the ownership and the responsibility. Is that clear?
Yes. Yes.
Okay, so this is our service point. What happens um what happens in step 4? Who hasn't answered?
After the service point.
I can't see you, Luis.
What?
I can't see you.
Can you see me now?
No.
Give me a sec.
All right, somebody else. What happens in step number 4? Megan.
Okay.
The wires become the service entrance conductors. Those will have a drip loop, and then they'll go through the weatherhead or gooseneck down into the service mast.
Okay, say this is your house. This is your weatherhead or your gooseneck. I now have my service entrance conductors, okay? Not to be, remember to keep these straight. The service directly from the transformer, we are dropping service. So these are the service drop conductors, okay? After the service point, we have the service entrance conductors because these are the ones that will be entering the house. So let's just say they go up here like so. And before we enter the gooseneck, Miss Sims, what do we have?
The drip loop.
Yes, ma'am, the drip loop. So we have our weatherhead or our gooseneck. And so this can be attached to the roof, like how I'm showing here, or it can be attached right here, like on the exterior of the home. But from here, our conductors travel down through the service mast, which is just, it looks like a tube. It's conduit that's protecting our service cable, which are 2 hots and our neutral, protecting it from the elements. Okay, so now I'm at step 5. Luis, I can see you now. What happens at step 5?
It goes to the meter base.
Yes.
Go to the utility base measures the electricity to charge the homeowner.
That's correct. That's absolutely correct. So this is our service mast. This is our meter base, which contains our meter. What happens in step 6?
The power enters the service equipment. That's where you can disconnect and connect the electricity.
When we say service equipment, what word are you thinking?
Main disconnect.
One word. I said when we say service equipment, think
Control center.
one word, Cola. Panel. Service equipment, I want you to think because I want you to be able to visually follow this path. So when you hear service equipment, think panel. Yes, inside that panel, you will have your main service disconnect, but think panel, okay? So let's just say we got a basement here and our panel ends up on this wall of the basement. And so our service entrance conductors would come into our panel. And then in our panel, they would be connected here to a bus bar, which we'll get into in a second, and the neutral. So now we have our two hots and our neutral that's been brought into the house. Do you have this diagram in your notes?
Yes.
Does everybody have this diagram in your notes? Labeled and all the things.
I'm getting there. Yes.
Can you explain electricity's path into the home?
Yeah.
Okay, so now let's talk about this. When electricity reaches the house, it is entering again through our service cable here, and that cable has the several conductors, so our two hots and our neutral. Okay, so again, our two hot wires are our energized or our ungrounded conductors. Okay, these are the wires that are carrying the current into the house. Each hot wire is carrying how many volts?
120.
That's correct. When measured between the two, the voltage is 240 to power our larger appliances. Okay? So again, in our 120 volts, there's one hot and one neutral. That's for our standard outlet or light circuit. Your 240 volt is both of the hots together. Okay, these wires are always energized when there's power. So you should never touch the conductors if they're exposed because they're energized, meaning they have power, they are hot. Okay? Everybody got that? We are good conductors of electricity. Electricity will begin to flow through you if you grab those energized conductors. You understand? Okay. Then our neutral wire or our grounded conductor. What does the neutral wire do?
Carries the load back to the source.
Not the load, the current. The load is the device that it is servicing. So it carries the current. It's the return path for the current. This is what completes our circuit, right? So essentially we have, where's my color thing at? This is the constant flow. And then there will be a light bulb here or a receptacle and an outlet, and then the power from the branch circuit will go here, and then it will look to go right back. That is the constant circuit that we are running. So in a normal operation, whatever current leaves on the hot conductor should return on the neutral. Okay? And then number actually I'm gonna I'm gonna stop this. I could probably sell this. What y'all think? Kind of look like a Basquiat or something, like a little bit. Okay, let me bring back up the slides. Oop, those are- This is what I'm looking for. Okay, so now we're looking here. So again, in this diagram, we have our two hot wires coming from our transformer. And then we have our neutral wire or our grounded conductor is in gray. Coming service drop, service point, service entrance conductors, drip loop, through the weatherhead, down the mast, meter base, panel. Okay? So boom, we're right here now with the service equipment. Each each load or each thing that we are trying to power has what's called an equipment grounding conductor or an EGC. This is the safety wire. Okay, so it is not intended to carry current. When everything is working correctly, this green wire here is not intended to carry current. Its purpose is to create a path if there was a fault. So if something goes wrong in the electrical system and the current goes haywire, a short circuit or something like that, the EGC, our whole grounding system, but specifically this EGC, it is trying to give a path for that current back to its source. Because again, that energy is always going to be flowing and it will look for whatever is conductive. If it's you, if it's a copper plumbing pipe, whatever conductive material it can jump on and travel, it will. And so that's what our EGC is doing, giving a low resistance path for a fault current when there's an issue. Okay. And this path, that's what allows your breakers to trip and prevents other metal parts that you don't want to be energized becoming energized. Okay. So again, just one more time, we've got our transformer, our service drop if it's overhead, or our service lateral if it is underground. Our service entrance conductors, our drip loop going through our weatherhead or our gooseneck, down the service mast to the meter base, which holds the meter into the service equipment, or our panel where we have our main disconnect. The main disconnect disconnects all the power to the home. The service equipment also distributes the power throughout the house. Branch circuits. Okay. Our loads, the electricity finally reaches where it's trying to power, which is our load. Again, think your lights, think receptacles, your refrigerator, your AC, all of that. The devices that use it. Once the energy does its work, the current returns back via the what?
Neutral.
Via the neutral, completing the circuit. Electricity is always going to seek to take a complete path back to its source. I think in a book it talks about like dispelling a common myth about electricity seeking to go to ground. That is not the case. Electricity wants to go back to its source. Okay. And the neutral is what provides the path. When everything is working correctly, the neutral is the path, is that return path back. If we have an issue, some sort of fault, the grounding system provides another alternative safe path for our fault current. So any questions on electricity's path to the house?
I have a question. So
Uh-huh.
when we're talking about the service equipment, we're still on the outside of the house. That's not what we're like flipping breakers and stuff at yet, right?
No, it is. That's why I said think panel, because you are tipping in most. There's some places where those panels are outside, but in most cases, yes, you will be inside. This is where you go if you have something, a breaker trip or something like that, and you go and you want to kill all the power to your house, you would go to the panel, which would have the main disconnect, which is considered service equipment.
So is that because there's a picture in a book, right? And it shows, or I'm thinking about my mom's house. She has a panel on the outside of her house and then also on the inside of her house. So is that just it's not the other side of the panel. I'm trying to figure out what
It could be a sub panel.
Okay.
We'll get to that in a second, because we're going to talk about the panels, the type of enclosures, the type of panel boards, and all of that. And if you still have that question, let me know. Next we need to talk about the clearances. Of course there has to be clearances for our service drop conductors. We want them to have a safe distance over any roofs, decks, walkways, all of that kind of stuff, so that people can't reach them or access them. So first of all, a roof deck with pedestrian traffic. So if you have a some sort of roof area where people can go out and walk on, a deck, a patio, balcony, something like that, then the minimum clearance is 10 feet above the walking surface for your service conductors. A minimum of 10 feet if there is a roof deck. If you have a roof with the slope less than 4 and 12, aka basically a lower sloped roof, then the minimum clearance is 8 feet above the roof surface. So that means that your conductors need to be 8 feet above the roof surface for a low slope roof. And then for a roof with a slope that is greater than 4 and 12, or our steep slope roofs, the minimum clearance is 3 feet above the roof surface. Okay. And then at the edge of the roof or at the eaves, if the service drop crosses across the eaves, there needs to be at least 18 inches of clearance above the roof edge. Okay. So again, the idea is to keep the conductors from sagging onto the roof, the gutters, that type of thing. This we're inspecting it visually from the ground, because again, you are never going to attempt to actually touch the conductors directly. If the clearance appears, borderline close, I would document it and recommend further evaluation. This is a very common defect, again, on older homes that are in disrepair and have deferred maintenance. You will have the conductors, the lines will, sagging over time due to the weather, or again, just to the edge, to the age of the actual house. So again, if you have a walkable roof deck, 10 feet, low slope roof, 8 feet, steep roof, 3 feet, and at the edges or the eaves, at least 18 inches. Okay. We have the same clearance requirements from windows, doors, balconies. Basically, think anywhere where there could be people. Okay. So any window that can open, if you have an operable window, then your service drop needs to be at least 3 feet horizontally from any window. So you see here, number one, 3 feet, 3 feet of clearance, 3 feet of clearance required because that is an because these sashes open. It's an operable window. If you have a fixed window, then they can pass closer than the 3 feet. They just want them to be secured and actually not touching the surface. So that's number 2, where it says the clearance is not required because this is a fix. And then your clearance to doors is, again, you want to see 3 feet of horizontal clearance from any door or opening where a person could be in contact with the surface drop. Okay. And then lastly, as it relates to clearance, this is a test question, so you should memorize it. The service drop clearance is above the ground. So the minimum clearance when you're talking about the ground or a walkway, a minimum of 10 feet above the ground. So this is the lawn, the sidewalk, yards, 10 feet. And just think, this is the area, think closer to the house. Like, memorize this basically in the form of this diagram. So the area that's closest to the house has the lowest clearance requirement. The further away that we get from the house, the higher it goes. So next, our residential driveway, a minimum clearance above the driveway is at least 12 feet. And then the minimum clearance above public streets is 18 feet. So we start closest to the house with 10. Think sidewalk, walkway. The further that we get away, the driveway is 12 feet, and then a public street is 18. Any questions on the clearance requirements? Okay, let's get into the panel now. So the panel is basically, again, it's like the control center. It's the central hub for the whole entire electrical system. This is where the incoming power, like we just learned, comes from and is distributed through the house. And it's also where some of the safety features are to protect us from, again, fault currents and different things like that. So we already talked about surface equipment, referring to the components that serve as a disconnect, and that they are the components that allow electrical supply to be distributed throughout the house. So you will sometimes hear it called main disconnect, main breaker. These are all the same things. Okay. One of the key rules for your service equipment, this is also a test question, is the 6 handle rule. All power to the house should be able to be shut off with no more than 6 operations. So no more than 6 switches, 6 breakers, fuses if you have them. You should be able to kill the power within 6 operations. And then enclosure. So an enclosure is actually the box. So what we call the panel box or the electrical panel or the main panel or whatever, it is technically an enclosure. Okay. So it is the box that is holding all of the electrical components. It's usually made of metal, galvanized. Okay. So the enclosure is holding or containing all of the energized parts and protecting those electrical components. Again, in slang terms, this is the electrical panel, this is the breaker box. All of that just refers to the enclosure. So the enclosure is the container, and then the panel board is the actual machine inside. So most residential enclosures, like I said, are made from galvanized. You can have non-metallic, like fiberglass and stuff like that, enclosures that are approved for indoor and also damp areas, because to Miss Sims' point, you can have outdoor enclosures. They have to be rated for that, but they can be outdoors. They can be, your enclosures, whether in or out, can be installed directly to the wall, or it can be installed on top of a wall surface. This is like what it's like when you have a basement. And then we have three main enclosure types. So the meter main enclosure, okay, when we say enclosure, again, just think box. This is where you have the meter, the main disconnect, and a panel board in a single enclosure. Okay? So this is what you see here. You see the meter, the disconnect is somewhere on here, and the panel board for all of your branch circuits are located in one enclosure. This is a meter main. This is common in newer homes. Does your mom have a newer home, Miss Sims?
Yeah.
Yeah. Okay. So
2000.
okay, so that could be why this is what she has outside.
No.
What does she have?
But hers is from it comes from underground, so I'm thinking that I might be looking at, I guess, where it connects from the underground.
Oh, okay, yeah. So that's not an actual panel then.
Okay.
Yeah, so her panel is still on the inside. So then that takes me to number 2, the main breaker panel board. This is the most common residential setup, which is this one right here. You have a main breaker or a main disconnect that shuts off all of the power to the home. And then you have all of your branch circuits here that distribute the power to the home. This is most common right now. And then you have your main lug. So the main lug, there's no main breaker inside. So these panels are being fed by another system, essentially. Like a sub panel setup. Okay, so these are our enclosures. And then we have our panel board again. So this is the main distribution point for our electricity. Okay, we have single bus panel boards, which are again most common today. This one on the left, where the main breaker again shuts off all of the power. So this up here is the main breaker, and it can control the power to all of the circuits. You can kill it in one motion. That breaker is again typically, it has to be a minimum of how many amps?
100.
That's correct. A minimum of 100. So with the main breaker, you have your power flowing through. So this is our 2 hots and a neutral coming in from outside. The power is flowing through the main breaker down to your bus bars. And then you have, these are again your branch circuits here that are protected by the breakers. And then you have your main lug. A main lug panel board again is receiving I said main lug for enclosure. I meant a main lug panel board. It receives its electricity from feeder conductors that's coming from another panel. So these are your sub panels. Okay, they are downstream, or they come after your service equipment or your main panel. Because they are sub panels, inside of the sub panel, neutrals must be isolated from the grounds. Write that down. You may not understand it right now, but you need to know it. In a sub panel, neutrals and grounds must be isolated or separated. Neutrals and grounds must be isolated and separated in a sub panel. Now, our panel clearance requirements for the actual panel itself. They want you to be able to actually access this panel for servicing and all of that kind of stuff. So again, these are code required. This diagram right here is straight out the ICC. So these are code requirements. So your working space depth, a minimum of 36 inches clear space in front of the panel. So in front of the panel, there can't be anything else for 3 feet. Working space width, a minimum of 30 inches wide. As you can see here, headroom clearance, a minimum of 78 inches or 6'6". And then the door swing for your panel. The panel has to be able to swing open 90 degrees. For your inspection purposes, the panel has to be accessible to you without having to move furniture, old appliances, personal items, basically. You should be able to walk right up to the panel and open it up freely, and the door open at least 90 degrees, and it should be reachable as well. I forgot to say, your maximum breaker height is 79 inches because they don't want you to have to stand on a ladder to be able to access the breakers in case you had to shut it off. Sometimes panels are locked, but they're supposed to have easily accessible keys. All of these are either defects or limitations. If you're in a house and you're trying to inspect the panel and you can't get to it due to personal property or whatever the case may be, then that is a limitation, and you would take a picture of why, and you would disclaim, I was not able to inspect the panel and the service equipment inside due to personal property blockage. Snap a picture and let them know. This is one of these things where I try to, and we'll get into this after you finish and all that, but on the business side of things, when you're setting up your inspections with your realtors and things like that, this is one of those things that I remind the realtor, hey, make sure all of the main mechanicals are accessible is typically what I say. The water heater, the furnace, the electrical panel. Make sure there are no pets on site. Make sure nobody parks in the driveway. These are all things that I have told to my realtor. So typically the realtor will then convey to the client, because that's a huge part of the inspection. Speaking about the electrical panel, that's a huge part of the inspection that if I'm not able to access it, I have to disclaim. And that's one of the areas where we typically make our most money, because there's typically something wrong with the electrical system, and not to mention that, but it could cause the biggest risk from a safety perspective. So it is important for you to actually be able to access the panel. Are you required to open the panel? Are you required to open the panel?
No.
Why not?
I don't know.
So does everybody agree? No, you're not required to take the panel. Does anybody think we are required to open the panel?
I think we are.
I think we're
We are required
You
to
have
open
to.
the
How are you
They
gonna
go
check the
required.
breakers?
And you gotta see if you have your hot and neutral conductors. Gotta make sure they intact.
Well, if I flip the light switch on, I mean, I'm pretty much so safe to say I got two hots and a neutral, right?
Yeah, I think
What if your breaker's not labeled properly?
Oh, okay, Inspector.
it's also part of the SOPs.
So I will say this. When it is safe to open a panel, you should open a panel, because to you all's point, you can't assess the wiring or anything, the grounding, anything, unless you open a panel. By open a panel, we mean moving the dead front. So if it is safe for you to do so, you should do so. However, if there is any condition that makes it unsafe, then you should not, and you should document your decision if you decide not to open it. So a lot of times for me, most times the panels are in the basements in old houses, and they're often leaky. Well, what if there's a water leak right at the front of the panel? Or what if there is signs that the panel itself has had moisture intrusion? Would you open it?
No.
I don't either. Now you have some people who would say, they may try it. So again, these are some of the subjective decisions that you will have to make when you're out in the field, but it's important that you know the implications of both. Okay? So Some of your state SOPs might require you to open it, but ultimately it comes down to you and the decision that you make about the safety of yourself first, and then also the building, right? So we got a responsibility to look out for us, our physical safety, as well as the safety of the building. We don't want there to be any sort of electrocution. We don't want there to be any arc flashes that could start a fire. We don't want to have any of that. So you will have to assess the situation and make a decision on whether or not it makes sense for you to open the panel. And when we say open up the panel, we are talking about removing the dead front cover, which is just the front place or the face plate of the actual panel. Is just keeping everything on the inside of the panel, again, the energized parts, safe. Okay. And when you remove the panel, then this is when you get to actually visually see what type of conductors or wires, the sizing. We can see what's going on with the neutrals and the grounds. We can see our lug connections. You can see if there's any evidence of any overheating or any burning, corrosion, rusting, all of that kind of stuff. So again, it is important that you remove it and that you are able to see it. So the openings in the dead front are for the breaker handles. So these openings here, this is where your breaker handles, and they are sized basically to limit access. They don't want you to access the live part of it, just the actual handle. The dead front is typically secured, depending upon the type of panel, by screws. Sometimes they're typically six, two at the top, here, here, and here. And so you have to remove those six screws. So again, this is where paying attention could literally, be the difference between you getting fried, dyed, and laid to the side and not. Okay. You have to always assume that the panel is energized, meaning that it has power. Okay. It's important that you should always, I'm guilty, I don't always wear eye protection, but you should always wear eye protection, because that's why they're called accidents, because you didn't mean for them to happen. You didn't know that they would happen, and you want to be prepared. So eye protection, insulated gloves, and you have to be careful when you are removing the screws, because again, you're going to be removing them one at a time. This is where you use your electric screwdriver. You have to be able to remove the screws, sort of hold the panel. Some people use these magnets where you can magnet on, but I don't. I just stuck it out using my hands. So you have to remove the screws and sort of hold the panel so it doesn't fall off as you are taking off the screws. And then what has been my biggest thing is losing the screws. Okay, because you're trying to take them out, and if one fall, like, just imagine this. You can only imagine what the floor in this basement looks like. Okay, so dropping them somewhere you can't find, God forbid. I almost dropped one time down a drain, like all type of stuff. So you've got to be careful that when you remove the screws, you actually secure them and don't drop them anywhere. And then when you do remove the dead front cover, you got to listen. Do you hear any buzzing? Do you see, again, any signs of arcing, which is basically overheating, the step before fire? All of this stuff may suggest that the panel may be unsafe. So you got to really, pay attention when you are removing the dead front cover. Okay. And so then inside of our panel, we start at the top. We have our main breaker. This is the primary shutoff switch. So this, again, is akin to our main water shutoff. It's also, again, they call it the service disconnect or main disconnect, whatever the case may be. But when you turn it off, you stop flow to all of your branch circuits that are in the panel. But you do have to remember that the incoming service conductors are still energized. Remember, because they're getting their power from the transformer. If you cut this, yeah, you are stopping the power for the branch circuits, but these conductors will still be energized. Okay. In most panels, this main breaker will be at the top. However, it could end up being at the bottom. Sometimes we have DIYs and all that kind of stuff. It could be at the bottom. This is where you will also find the amp. You'll find an amp rating on the main breaker, and that typically is what represents that total electrical capacity that the service can safely carry, which we need it to be a minimum of how many amps?
100.
How many?
100.
That's correct. A minimum for our residential homes is 100. Now, in real life, 100 amps is not nearly enough for all of the stuff that we be having going on in our houses. All the computers and the game systems and it is and it that is really not enough. So newer homes, it is common for you to see a 200 amp service. Okay. So how we find that minimum, how we find the capacity or the amperage for the house is right here at that main disconnect. You see how it says 100. Do 100. All right, so next we have our bus bars. These are the metal strips that are in your panel, and they basically help distribute the electricity throughout the entire system. So you have a couple different bus bars. Okay, you got to think of a bus bar like a highway. The bus bars are the main highway carrying electricity through the panel, and then you have your circuit breakers here, which are like off ramps, right? You could take power off of the highway and send it to a certain room. We have different types of bus bars. Okay, in our residential electrical panel, you will have a neutral bus bar. This is where all of the white neutral wires will connect. What does the neutral do for us? What are our neutral wires doing?
Carrying the current back to the load.
That's correct, acting as a return. In a main service panel, the neutral bar is what we call bonded to the panel, to the cabinet. In a sub panel, the neutral and ground bars must be what? Isolated, separated. The neutral and ground bars in a sub panel. Okay. So here on the right, this is a neutral bus bar. We know so by the white wires that are terminating on this bar. Here is also a neutral bus bar, but there are some ground wires terminating on this neutral bus bar. Is that acceptable? Yay or nay?
No,
Why not?
because the neutral returns the electricity to the source,
That is true.
and the grounded, which is the copper, right?
Correct.
That doesn't do the same thing. Hold on.
Can the neutrals, this is my neutral bus bar. I've got ground wires, these bare copper wire. Remember you asked me earlier, see, what is bare copper? Literally just a bare copper wire. These represent our ground wires. In our main panel, can the neutrals and the grounds terminate on the same bus bar? Yay or
Yes.
nay?
Yes.
Why?
Yes. Because they're both grounds.
I think no, because it's the ground carrying the current, and the neutral is carrying the current to a certain place. The neutral is carrying it back to the source.
In a normal operating system, will my ground wire be carrying current?
No.
Why not? Why is the ground wire not carrying current?
It's not part of the circuit unless there's a ground fault.
I
But
like
guess
that.
it it.
I like that. Okay, not necessarily about the circuit, but the ground wire is only going to be carrying current when there's a problem. Think about the TPR valve, right? There's never going to be water coming out of the TPR valve unless there's a problem, unless the tank reaches what temperature
210.
or what pressure?
150.
Yes. That would be the only time in a dire situation would there be water coming out the TPR valve. It's the same thing with our ground system. In normal operation, there should not be any current traveling on the ground system.
So the grounding protects the electrical aspect, the equipment, and the bonding is for like protection for individuals.
No, not quite. But let me get there to grounding and bonding, and I'll put that all together for you. Right now, I want you to understand that the ground system, the grounding system as a whole, your grounding wires are it's a safety net. It's only in a worst case scenario where there's an issue, a fault, will we have current traveling on the ground. In a normal condition, when everything is okay, we will have current traveling on the hot and returning on the neutral. If for some reason, again, a fault happens and we cannot return on the neutral, that's when the ground system steps in and say, hey, I got a path directly to ground. You got it?
So where would the grounding lead to? It's not supposed to be here. Is it going? Where would it go?
Okay, give me 1 second. I'm going to get to the grounding system and we're going to put that
Okay.
all together. So let me hurry up then. So clearly y'all want me to hurry up with my little speech. So let me get on to the grounding and whatnot. Okay, the last thing is lugs. Okay, so these little mechanical clamps here or the screw terminals, what holds the conductors in place within your panel, these are lugs. So these are supposed to have a real secure connection with the wire, because again, this is how we are transferred, creating that circuit or that clear path for our current. So you've got your main lugs here where you have your circuit breakers, or I mean the let me see, main lugs. So these are your main lugs here where our two hots are coming in. And then we have our breaker lugs here, which are this screw here, this screw here. These are our breaker lugs. And then we have our neutral bar lugs here. And then we also have our ground bar lugs. Okay. So again, a lug is just this screw. This is the connection point for the wire. Next inside of your panel is the bonding jumper. Okay, the bonding jumper is just a connection point inside the panel that connects the neutral bar to the ground bar. Just write that down in your notes so you have it. We're about to make it plain in these next couple slides. The bonding jumper is a metallic connection. So it's a metal connection inside of the panel. It connects the neutral bar, the neutral bus bar, and the grounding bus bar. I'm gonna skip. Okay, so let's get into grounding and bonding. So again, electricity wants a complete path back to the source. Okay, and the grounding and bonding system is what basically makes that happen. So grounding, which is also called earthing, is a connection from the electrical system to the earth, literally. Okay, and you use a grounding electrode conductor to do so. So grounding is a connection, a deliberate connection from the electrical system to the earth or to the ground by way of a grounding electrode conductor. Okay? Bonding is not an electrical term or an electrical concept. Bonding just means exactly what the word means, connecting all of the medical metal parts that could become energized, connecting them together so that again we can complete that path to ground. So when you think of bond, think of literally just a connection, like literally what the word means, to bond with somebody, to connect with them. We are connecting metal components that we don't want to be energized. Do you remember when we were learning about plumbing and we were talking about bonding the plumbing lines and why that needed to be? Well, that's because the plumbing lines were made of copper. Copper is a very conductive material. You will find here that when we start to talk about the wiring, most of our branch circuit wiring is copper because it does a good job at carrying electricity. It doesn't know that, well, this particular copper tube is supposed to be carrying water and this one is supposed to be carrying electricity. So that's why we have to bond those plumbing lines into the bonding system so that if we were to happen again to have a fault, we don't want to have current traveling on our copper plumbing lines. Okay? So it is creating this path. We're connecting everything so that it can travel on that path to ground in the event of an issue. Okay, so the grounding is what connects the system, the whole electrical system, to earth. And then the bonding is what ties all of the parts together so that they can, so again, in the case of a fault, you have a solid return path. Everybody got that?
I have a question.
Uh-huh.
So in the review, you had the 2 copper pipes and that water heater, and you had another copper piece that kind of went like a rainbow that was connecting them. That was the bonding
Jumper. That was the bonding jumper.
jumper.
Yep.
Okay.
So we were using that copper wire to connect those 2 pipes together. That act is bonded. Those pipes were bonded. What we did it with was the bonding jumper. Okay. All right. So let's talk specifically about grounding. Okay. So we ground the system to protect people and equipment. If you have again a hot wire that touches something metal or something that is conductive, the grounding system is what gives that electricity a shortcut to be able to leave before we have an issue. Okay, that path is what helps again the breaker to trip and kill the power before anybody gets shocked or before the wire has a chance to overheat. So if you had to describe grounding, grounding is simply how we connect the home's electrical system to the earth. So when I ask you, what is grounding? What does grounding mean? I want you to say, Nita, grounding is how we connect the home's electrical system to the earth. We're doing this on purpose to give the electricity a safe way. In the case that it get out of whack and it's too much, we're giving it a safe path. Again, think pressure relief valve. If the electricity builds up where it shouldn't, grounding gives it somewhere to go safely. Now, there are 2 ways that grounding works. We have system grounding, which is this is done at the main panel. This is how the main connection between the wiring system of the house and the earth. So system grounding is again the entire system. I can't get into that right now. And then we have equipment grounding, which is grounding for our circuits. So this protects again all of the metal parts that our fixtures, our outlets, the frames of our appliances that again are metal and could become energized. Our equipment grounding is protecting those. These are where we have our green or our bare copper wires, those equipment grounding conductors. So if a hot wire were to ever touch metal, the grounding wire carries that current straight back to the panel through the bonding jumper. And then the breaker trips and kills the power. So that way the person doesn't become the path to ground. Because again, electricity, it doesn't care where, it just wants to flow. And if you are a conductive material, you could become a part of the path. Okay? So this is why our neutrals and our grounds are only connected together one time at the main service panel. Our neutral is supposed to be carrying our current back to the source. When we say source, we're speaking of the transformer. Our neutral is supposed to be the way that we're carrying it back. But if there's an issue, then our grounding system would need to step in and provide a path. Okay? Now, what makes up our grounding system? Think of it like a chain. Every link has a certain job. And if one chain is missing, then the whole system can't do its job. So we start with the grounding electrode. I mentioned this earlier. This is the part that's actually in the ground. Have you ever heard anybody say a ground rod? There's a ground rod there. I see a ground rod. The ground rod is the grounding electrode. It is actually in the ground. So we are connecting our home's electrical system to this ground rod outside, which is called, again, a grounding electrode. You can have different types of grounding electrodes, but the ground rod is the most common type. It's going to either be steel or copper, at least about 8 to 10 feet long, and it's driven into the ground. So you can see just a lot of times the top of it, where you'll literally see there'll be like a little loop, and there'll be a copper wire that's connected to that ground rod. Ground rod is the grounding electrode, or the GE. Say that out loud to yourself. The ground rod is the grounding electrode, the GE. The ground rod is the grounding electrode, the GE. It is outside. It is in contact with the ground. Okay. Then we have the GEC, the grounding electrode conductor. This is the wire that connects the grounding electrode or the ground rod back to the neutral bar that's inside the main service panel. So this is the connection point between our panel and the grounding electrode outside, the GEC. It is a copper wire. It is typically thicker than most of the other wires that are going to be in the panel. So if we look at this picture here, these two here that are thicker, these are the GECs. So on one end, they terminate here on the bus bar. And then if we were to follow this all the way through, it would be connected to the GE.
Grounding electrode.
That's correct. Yes, sir. Okay. So typically like about a, you won't know the wire size, but a 6-gauge wire. It just has to be a thicker wire, because again, remember, we needed to be able to carry the current in the event of a fault. So it's the bridge between the wiring system in our home and the earth. If this wire is loose, if it's not properly attached at the lug, if it's corroded, if it's missing, then we break a link in our grounding system chain. How would the current get from the panel outside to the ground or to the GE, lest we have a GEC? And then lastly, the EGC, or the equipment grounding conductor. This is the green or bare copper wire inside of our branch circuits. These are the wires that connect every outlet, every switch box and every metal fixture back to the grounding system. Okay, because remember, we got our GEC will connect the panel to the GE. But don't we need grounding protection at our receptacle, at our light switch? How would those light switches be connected to the panel that could then be connected to the GE, lest we have an equipment grounding conductor? So every time you look at a switch or a light or receptacle or whatever in your house, that load has an EGC that is connected back to the main panel. Everybody got it? You down with GEC? Yeah, you know me. Connect to the ground. It's a party. Hey. So we've got the EGCs that are connected to the grounding bar in our main panel, where we would have our GEC terminating, and our GEC would then connect us to our GE or our ground rod, which is outside. That is our grounding system. See, does that answer your question?
Yes.
Any questions?
I had a question about the breaker.
Save it till Friday, because I ain't even taught you about breakers yet.
I mean, the bus.
Okay, what?
Okay.
Words mean things.
When operating like the bus, it has the switches. If you're in a residential home, like say you're inspecting a home, and the electricity is already there, you don't operate that, do you? It's like you wouldn't operate the switches.
You are talking about the breakers. You're talking
Wow.
about the breakers, and no, you don't operate them.
Okay.
You don't turn it off and then turn it back on. You don't do that.
Okay.
We're not operating any of this equipment. We are visually inspecting, observing, and reporting on it. Okay, so the last thing with our grounding system is our grounding bus bar in the panel. Remember, we just saw a neutral bus bar. Well, we can have a grounding bus bar as well. Again, just a metal strip that's inside the main panel where all the grounding wires connect. So if I'm looking at a panel, how will I know if I got a neutral bus bar or if I have a grounding bus bar?
The wires.
Say more.
Green and copper wire.
Say more.
The grounding will be copper. The neutral wires will be white.
That's correct. So if I see a bus bar with all white wires terminating, I know this is my neutral bus bar. If I see a bus bar with all either green or bare copper wires terminating, I know this is my grounding bus bar. Now, can I have neutrals and grounds terminating on the same bus bar? Who am I getting an echo from?
Can you repeat that?
Can I have neutrals and neutral wires and ground wires terminating on the same bus bar inside my main panel?
Yes.
Why?
Can we just go?
I'm gonna get the answer one way or another. Does everybody agree? Can you have neutrals and grounds terminating on the same bus bar?
No.
No, I agree.
You don't agree, Cola?
Yes.
Why not?
I think with the way the boss back, you open up the thumbnail, you have to have it. And just there's a specific configuration to go, and the neutral has to stay away from those control. it's in the main panel.
Correct.
So they can be on the same, they could terminate on the same bus bar in the main, but not the sub.
Correct. But I want to know why.
Because the grounding goes back to the earth. And the neutral wires brings it back to the source.
Okay, so I don't understand what that matters. What is that? How does that relate to if I can have them both terminate on the same bar?
Because
Think about, hold up. Think about the main bonding jumper. What did I say the main bonding jumper does?
Keeps the current in the same. Yeah,
Don't that, oh, this grounding and bonding got y'all excited, huh? I should have been talking about this. Say that again in your words, Cola.
Connects us to connectivity between metal.
Connective. Wait, what did you say, Cola?
You were asking a question about the bonding jumper, right?
Right.
Bonding jumper. Yeah. I'm saying it's a conductor, so it's still connectivity between the metal parts.
So what does it connect between in the main panel?
Balls back.
Huh?
You say the balls back.
The bonding jumper is connecting what? The neutral and the ground. So if the bonding jumper is connecting the neutral and the ground, wouldn't I be able to have neutrals and grounds terminating on the same bus bar because they are bonded together?
Yes.
Oh, okay. Great. Thanks. So in the main panel are neutrals and our grounds. So you could have a bus bar that has neutrals, white wires, and ground wires, bare copper or green wires. This would just be a neutral grounding bus bar because you have both. Only in the main panel. Because in the main panel, the neutrals and the grounds are bonded together anyway to allow a path to clear a fault. Does that make sense? Yes, no, maybe so.
Yes.
Okay. So in the case of this diagram, again, we got our power leaving the transformer, our overhead service drop. It travels along our two hot wires and our one neutral wire. The wires that are entering the house, the hot wires each carry 120 volts. Together, they can supply 240 volts for the larger appliances. Excuse me, the electricity passes through the meter so they can count it and charge us. We get to the service equipment. Okay. And then in our panel board, we have a GEC. Where would I look to find my GEC?
Would you see it at the GE? Would it be connected to the GE outside?
Okay, and then what about the other end?
It'll go to the system,
Where at specifically?
the bus,
Which bus?
the main panel. Bus. My words are mixed up.
I mean, I like what you're saying. I just want you to say the right thing. Okay, so if our GEC, you told me on one end is connected to the GE or grounding electrode that's outside, And then the other side, you say the system. I agree. You say a bus bar. I agree. Which bus bar? Is it the neutral bus bar? Is it the grounding
The
bus?
grounded bus bar.
What if I have neutrals and grounds on the same bus bar? Would it still be terminating there?
As it's bonded. Right?
Well, the bonded part just means that the GEC is connected to the bus bar. But if I have a bus bar that has white wires and bare copper wires, could I also find my GEC there?
Wouldn't that also be copper?
What do you mean copper?
Because it's grounded.
Yeah, it would be copper, but can I find the GEC there?
Yes, because they'll be thicker than the other wires. That's what was on the diagram, wasn't it?
It would be thicker. So you're saying yes, I could find the GEC on a neutral grounding bus bar.
Yes.
And that is because why?
Because they're bonded.
Yes, because the neutrals and grounds are bonded at the main panel. That's correct. Okay, let's look at this last one. Okay, so this is how grounding and bonding connects everything. So we got our power coming into the main panel, okay, via our two hot wires. They don't show the two hot wires. They only show the grounded service conductor, which represents what?
The neutral wire.
Yes, the neutral. Grounded service conductor just represents the neutral. Okay, so here is the neutral wire coming in. And so, what type of bus bar is this?
It's a main panel.
What type of bus bar is this?
Neutral grounding bus bar.
Just a neutral bus bar. Because we only, as far as we can see on this diagram, there's only a neutral wire. Okay, so if it's only neutral wires terminating on it, it is a neutral bar. Okay? So during regular, everything is cool, normal operation, the neutral is the return path for the electricity that's flowing through the circuits. Okay, so this is kind of like, I think their way of showing the two mains coming in, these are breakers, it goes out, powers the load, it comes back via the neutral, terminates on the neutral bus bar by way of the grounded service conductor that's being dropped in, goes back to the source. That is the circuit. Make sense? Now, we have our GEC, or our grounding electrode conductor. This is the orange wire, okay? This connects the panel's neutral bar to the grounding electrode outside. So this is where we would see that thicker copper wire. So to C's point, she said it's connected to the ground rod. Yes, but it is also terminating on my neutral bus bar to connect. Okay? So now, if the current is supposed to be coming back here and it can't for some reason, there is a path or a connection to ground. Okay? Then this orange bar here is the main bonding jumper that's inside the service panel. This is what bonds the neutral bar to the ground bar. And it's bonding both of these to the actual enclosure, because this is metal too. It could become energized. This is why you've got to be careful, because if you're not and something is going wrong and you reach out and touch the panel, just the panel, the dead front, it could potentially be energized. Okay, so the bonding jumpers connecting my neutral and my grounding bar. Okay, so it's sort of like we shaking hands here between the neutral and the ground so they can work together. Then I have my equipment grounding bar, or my grounding bar inside of my panel where my EGCs terminate. So all of my equipment grounding conductors, or my EGCs, from my outlets, from my switches and appliances, they connect here. They come back to the grounding bus bar. Are these wires carrying current?
Not under normal conditions.
That's correct, because this is safe. This is safety only. This is my pressure release valve in case it's too much. This here is my normal return path. Okay? These wires, my grounding wires, are not carrying current. They're waiting for a problem. They're waiting for a fault. When that happens, the fault current will flow through these wires back to the panel. Okay, so whenever you have a branch circuit, and we'll talk about this more on Friday. Whenever you have a branch circuit leaving the panel, it is going to have 3 wires. Okay, it's going to have your hot, it's going to have your neutral, and it's going to have your ground. So if you were to take out, unscrew a switch, the light switch, you would see a hot wire connected to that switch. That would probably be black. You would see a neutral wire that would be white that would be connected to that switch. And then you would see either a bare copper or a green wire that would be connected to that switch. Does this make sense? The neutral carries normal return current. This is our normal path. We got our 2 hots here coming in, our breakers, our branch circuits, out to the load, power it, boom, the light turns on. Okay, now it wants to go back home. I'm traveling on the neutral, no problem. I terminate here, boom, we transfer, terminate, I'm back to the source under normal operations. The grounding system only carry current when there's a fault or a problem. Up, I'm not able to get back via the neutral. I need to travel now as an alternate path because it's going to keep traveling. Something is going to get energized. Okay. So now I'm traveling on the grounding system, terminating to the grounding bar here in the panel, which is connected to the neutral bus bar, which is connected safely to ground outside. This can't happen unless everything is connected or bonded. The bonding is what creates the path. That's all bonding refers to, is the fact that these metal object or components are connected so that if there is an issue, we have another path without any breaks to send the current to the ground. What questions about the grounding system do you have? God bless you. No questions? Are you confused? Do you understand? How do you feel? Let me know. Bree, what you feel? Bree had to sit up, or Bree normally be laid back. She had to sit up on the edge of the bed for this grounding and bonding, boy.
Listen, you're gonna have to use some more time. I ain't gonna need that.
It's a lot. It's a lot. I trust me. I know. The first time, and mind you, again, I didn't even have nobody to explain this to me. I'm like, what? What are you talking about? Or so, are there any questions? Any spots where you feel blank? You should use. Go ahead.
I mean, I'm just digesting it, but my worry is taking off that box because I'm just thinking that, or the dead front, because there's power go into it. So how do you know? I saw in the book where it was like, touch it with the back of your hand. How do you know if there's something that is possibly wrong before you take it off? Besides, I mean, seeing water or something like that, like
Seeing some evidence of it, hearing like a buzzing sound, of it indicating a trip breaker or something like that, feeling that warmth. That's why they say touch it with the back of your hand. I mean, those are, you won't really know. Those are the evidence that things could be going on. But there's no way to really know until you see it. I will say that in most cases, um like this. Like before I took this dead front panel off, like I already knew to be super precautious because it was a mess. You know what I mean? Like, and so when I took the dead front off, I did find defects and issues, but there was nothing that I observed at the time of this inspection that would have caused me or the property immediate harm or danger. So it is, I will say, it is definitely, it took me a few inspections to get comfortable enough to open up the dead front. I just keep it a buck. Like I was scared to death. Cause again, I didn't know what I did, how I really got comfortable with electrical is I went out with the guy that I used to pay to do my electrical work. I went out with him and had him show me, and and that helped me to get a little bit more comfortable, and then it was no problem. So I will acknowledge, like at the beginning it probably will be a little intimidating to remove the cover, but um it's important because look, this is what you see when the cover is off. So these are two hot, let me zoom this in a little bit. These are our two hots coming in, connected, our main lugs. This is the main disconnect. See here, main. And then this is our neutral connected over here to the neutral bus bar. Okay, that's where we start. And then we've got our different branch. So we've got a neutral grounding bus bar over here because I've got white wires as well as green wires. And see down here, that thick one? What is that?
The copper, this should GEC.
That is in fact the GEC. So it is terminating here. And then where is the other end connected to?
The GE.
The GE. That's correct. So all that you need to see, all this, because you need to be able to, as much as you possibly can, verify that they have a grounding. The grounding system is their safety system for the electrical. So it's important that you are able to, again, visually confirm or deny that. That's what remove. Go ahead.
What is that orange wire
Down here,
on the right?
these are branch wires. So
Okay.
on Friday we will talk about different wiring types. Romex, the most common type of residential wiring, is again color coded. So the color will correspond with a size of wiring. Okay. Any other questions?
One more question.
Uh-huh.
Is that rust on the right side on
Where?
the thick wiring?
This is
Okay.
actually cloth wiring. So this is a sheathing that is cloth and is like unraveling. That the brown stuff is what you're talking about?
Yes.
Yeah, it's cloth and it's unraveling. Cloth wiring. Frayed, which is a defect because it is a fire hazard. Okay, so on Friday, we will start with our OPDs, overcurrent protection devices. Then we'll get into the wiring methods, our receptacles, and our switches. And that would be electrical. See, that wasn't that bad, was it? I haven't seen him saying, nah, pump your brakes. Was it that bad?
I don't think so.
It wasn't that bad. It's just that I have no idea. I think that electrical is one of those things where you just
It's
automatically
brand
call
new.
somebody.
See, electrical is brand new. Like a lot of this stuff, like with plumbing and heating, a lot of these components you've at least seen, you familiar with, and stuff like that. Electrical, all we know is we flip the switch and we get lights. And if it's, when I turn on my computer, if I'm good, you don't think anymore about it. So it is like sort of like brand new. It's all foreign to us. My refreshers. What did y'all take from this the second time around that you didn't get the first time?
There were additional points that you mentioned in there. Additional details.
It definitely clicked better visually.
Good. All right. Homework. Your homework is the electrical worksheet. So it's the same thing as the plumbing and HVAC. It's just the electrical version. So there is the fill in the blank as well as the short answer. It is over the entire electrical. So there will be some things that we haven't covered. Again, our OPDs and the wiring that we haven't covered yet. That's included on there. That will be very, very good practice and review for you as we go into part 2 on Friday, and then for the final. Any questions, comments, concerns, expressions of joy before we dismiss? All right, let's end with your biggest takeaway of the evening. Let's start with Luis. What's your biggest takeaway?
Learning more how the electrical system goes. Like, this is like a big time refresher for me, and I obviously didn't take too much of it from the last alumni, but this time I feel like I just consume more and absorb more information.
Good. I'm glad you feel that way. Have a good week. I'll see you on Friday.
And Sunday, complete.
Oh, you be here on Sunday?
Yeah. I'll send
Okay.
you a message.
Okay, cool. All right, Bree, what's your biggest takeaway?
My biggest takeaway is just learning the electrical cycle, how it comes from the power lines into the house. So, yeah, I got a lot more studying to do.
Indeed. Have a great week. We'll see you on Friday.
I got to.
Megan, what's your takeaway?
Yeah, it's starting to click a little bit more, especially after reading it. I was really confused, and then I got a little bit better. But the hot wire to the neutral wire coming around in the circuit is starting to make some sense.
Good. Have a good week. Catch you
too.
on Friday. C, what's your takeaway?
I had fun learning.
Good.
I was thinking about being an electrician. But yeah, just learning all the different components, and it's not as hard as I thought it would be because I was real intimidated before I started this, but it's not that bad.
Good. I'm glad you feel like that. That's a win. Have a blessed week.
So far.
Hey, we claiming it. It's not that hard. We got it. We feel good. We not as intimidated. That's how we operate. Have a good week. I'll see you on Friday.
See you Friday.
Philip, show takeaway.
The bus bars, it clicked. I got it.
Good.
Yeah. Everything else I remembered. I couldn't put it exactly in words, but I remember how it all flowed.
How it works.
And
Yeah.
came in, with the drip loop. I mean, all that I had.
Good.
So and that's why when she was saying the notches, I knew exactly what she was talking about, because even last time I drew the notches.
Okay.
And this time I drew them this time too. So
Okay.
I knew exactly what she was talking about.
Okay. Good. I love that moment, like when it clicks. It's like That's a really good feeling. Even when one aspect of the thing, when it clicks, that's a really good feeling. So I'm glad you had that experience. Be good. Take care. We'll see you on Friday.
All right.
Peace. Miss Sims.
My biggest takeaway is that the electricity is trying to return to the source, because I really thought that. Well, I didn't know where it was going. I honestly thought, how they say it goes to the ground. I was like, okay, that's what it is, but it's not like that.
Right.
And now that makes more sense.
That's also why they talk about going outside barefoot to be grounded.
Yeah.
Because the idea is that there is electricity emanating from the core of the earth because of the current that we have inevitably sent to the ground. Now, I don't know about the science and all of that, but I walk outside barefoot just in case. I'm covered either way. Have a good week. We'll see you on Friday. Cola.
I'll stay in the service panel for me. I think the explanation did make sense. From the perspective of if it's safe as an inspector to like inspect that, I really need to lock that concept down. But I think the boss belt, the bonding jumper, I still need to like, okay, how do I open my panel tonight and look at it from the low side to the one. I think I did learn something different, understanding when it's safe to install the service panel. And I think every other concept I understand, when in the panel, I need to understand if I'm telling a customer the inspection on the service.
Right. Yeah, I think that's good. That's a good pickup. When is the test?
Test is Tuesday.
Tuesday. How do you feel?
I feel confident, and yeah. So I'm hoping everything goes well for me because I have a sick toddler now, and since I work from home, I might be. So
wait, say that again. You have what?
I have a sick toddler.
Oh, okay.
So I'm still there. I'm hoping. I mean, I know I have 48 hours to 24 hours to say, and if my time.
Okay.
So,
Okay.
So if we get a call to bring him to the clinic, that might make me postpone my exam.
Okay.
So
We'll pray for positive outcomes on both ends for the baby and for you as far as the testing. Keep me posted. Let me know how it goes.
Sure.
All right. Have a great week. We'll see you. Peace.
Thank you. Peace.
All right. Hopefully you all learned something. If you'd like to get some help like this to help you prepare for the exam, the NHIE study guide is available for pre-order right now. It's $100 pre-order. You get a 50-question NHIE style quiz to help you practice, similar to how it's just helping them practice. It will drop on November 3rd. When it drops on November 3rd, it's going to be more. So go ahead and pre-order now. And with that, I will wish you a good night.